everybody. I am Steve. This is a talk called Exploring Ruby through Rust, and we're going to have a lot of emojis, and we're also just going to talk about a lot of different stuff in general. So I'm going to be going into like a pretty deep dive on some things, but relatively quickly because we only have 40 minutes. So this is more like, I don't expect you to necessarily remember all of it because there are very few people who know this particular intersection of all of these different languages and things that I'm using. So it's going to be fun. This talk is sort of about this combination, as Bodil kind of said. I used to do Ruby and Rails a lot. I actually have a Ruby tattooed on my arm. I have a Perl camel too, because I did Perl before Ruby. But I've sort of gone from the Ruby world into now Rust, and I really like Rust. I'm working on it full time as my day job. I authored the first edition of the book, and I'm a co-author of the second edition of the book we're working on right now. And so I'm always trying to connect these different paths together. And also, briefly, before we get more into that, I also wanted to say, I really hate the tribalism involved in programming languages. I've always loved learning lots of languages, and I've never really understood the trash talk between them. So I really like Rust a lot, but it's definitely not a thing for everyone. So if you don't like Rust, that's cool. It's fine. And so we're going to be talking about Rust and Ruby and C all together in weird combinations, and also fundamentally a little bit about having fun with programming instead of everything being all serious engineering stuff. A lot of the work that we do or the discourse that we have about programming is focused on how can we build something that's better from an engineering perspective, but sometimes you need to do stuff that's terrible from an engineering perspective in order to gain insights and or experience with things and the freedom that's involved from not having to worry about doing the right thing. So there's a little bit of that too. So a long time ago, or not that long ago, I used to build applications, mostly in Rails and other things before that. And then as I got and built more and more applications, I started moving down the stack into building libraries. So I worked on Ruby on Rails for a long time and maintained a bunch of different Ruby gems. But then I started getting involved in working on programming languages. So that's my current day job now, working on Rust. And then I have a hobby project I'm just going to mention in passing briefly, Intermezos, which is building an operating system in Rust. And the pitch is kind of, JavaScript, let's learn how to build an operating system together. So it's like teaching operating system concepts to people who've never done low-level programming before. But I've kind of worked down the stack constantly. And I don't think that, people always think that the stuff that's farther down the stack than they are is magic, and the things above the stack are easy. But I've always found that kind of ridiculous. I think operating systems is easier than front-end development in many ways. But also, coming from a dynamic language background, we always talk about the systems programmers as being the ones who are the super hardcore programmers. But the thing is, even below operating systems, you get into the hardware itself, and that's a level below the software stuff. And then to really understand the hardware, you have to understand physics. But then once you start getting further down into the physics, eventually at some point we don't know anything either. So really it's not there's people who know lower level stuff and it's somehow more foundational, I don't think. It's much more of a, we all have our specializations. Computers are too complicated for individuals to understand fully. So I'm a really big fan of trying out different chunks of the stack and learning things, even if it's not what you always do. As part of this, we're going to do a little comparison between some Rust code and some Ruby code to show you briefly a little bit of it. And this is sort of a semi-real world story about one way in which Rust is actually being used. So there's this method that Rails provides on string called blank ? And what it does is you call this method on a string, and it returns if everything in the string is a blank character or not, according to Unicode. So this is how it's implemented in Rails, not with the actual comparison to Konnichiwa, but it compares a regular expression to the string that you give it. And so it's got the Unicode, enabled space stuff. The beginning and end are at least 0 or 1 space characters. And so this is an incredibly simple implementation because Ruby is awesome on expressiveness. But it turns out that it's actually really slow, and it's also slow in a way that's surprisingly significant. I still don't really understand why this is significantly slow, in the sense of So there's this, this project called Discourse, which is a forum software for doing stuff. And it's a Rails application on the back end and an Ember application on the front end. And they found that this method, for some reason, was a significant bottleneck in their application. And that's the part I don't understand. I could see why the regular expression would be slow. And so there's this journey to optimize it. So before we talk about how this optimization happens, I want to show you briefly, I have a Rust file here. I'm going to be doing a bunch of live coding so you can see how terrible I am at Vim. It's going to be great. So in here, actually, I'm in the wrong directory already. Yeah, I'm going to bump that up and probably, do you like the syntax on or off? Cool. I just switched color schemes to hopefully make this a little bit better. Okay, so Rust is a low-level programming language, and so normally you think that that means that you have very little abstraction capabilities. But one of the cool things about Rust is that it often feels like a high-level language, even though it's actually a low-level one. So this is a whole pile of code. Most of it doesn't matter that much. The core of it down here is in main. So this is a little bit of Russian. I was showing off the non-Latin characters when I do string stuff. But we create a heap allocated string from the string literal, and then check to see if it's blank, and we make a blank string and see if it's blank. So this kind of looks vaguely like some OO code that you may have used in other languages. It's almost the same as the Ruby, except for parentheses and there's a question mark. But the thing here is we can extend. Rust allows us through a trait system, so traits are similar to type classes in Haskell. They allow us to extend types with new functionality. So I defined an isBlank trait here with one single function, which is actually a method. So isBlank, we use explicit self in Rust, sort of like Python more than like Ruby, and it returns a bool. And then here's an implementation of isBlank for strings. So and this is the part that I think is the best. So it's self.chars.all, check to see if they're white space. So this is extremely straightforward. And of course, the isWhitespace method is built into the standard library in Rust. But this is a really high level feel kind of to it, right? We have a closure, we're passing it to an iterator, we're doing all this kind of stuff. So the core of this functionality is just this one line, and it's really, really easy to write. So in comparison, so that's what it sort of looks like, this simple regular expression match versus that iterator closure combo in Rust. But why is this Ruby so much slower? So the thing is that Rust actually executes as fast as a hand-rolled code does in C. So there's actually an implementation, I think I have a link to it later, where somebody implemented this in C instead, and it's significantly longer and stuff. So I thought I had that link before. Yeah, okay, I don't. I'm not going to search for it and show you. But there's like a 150-line implementation in C that's much, much more complicated and much, much more low level, but it ends up being identical to the Rust. And this is one area where I think that Rust is really neat, or when I talk to people from dynamic programming language backgrounds, sort of one of our initial pitches for Rust is it's just as low level as C is. You can do all this low level stuff. And a lot of people who program in Ruby, Python, or JavaScript are like, cool, I will never use that ever. Because there's a reason I'm not using C in the first place, right? So the idea that you can write this code that feels very high level but has the efficiency and the power of being low level is the combination that I find intriguing about Rust. Okay, so now I'm going to show you a little bit about how we can figure out exactly why that Ruby code is significantly slower and what it's actually doing. So we're gonna look at some source code for the Ruby interpreter next. So there's a couple things that matter a lot with Ruby internals, and there's actually a really fantastic book called Ruby Under a Microscope if you want to learn a lot more about what Ruby internals look like. But I have mostly learned it just through messing around on weekends. And so there's this include Ruby, ruby.h file, which is where most of the definitions for the things in the interpreter actually are. And this contains almost all of the interesting bits that you use when you want to write an extension to Ruby. And then there's these two structs, RObject and RBasic. Because C doesn't have namespaces, everything is prefixed with R or RB to make sure that there's no naming conflicts. RObject is kind of the equivalent of object in Ruby, which is not strictly speaking the base class, but effectively the base class of almost every object in Ruby, and RBasic is the true base class of all the classes in Ruby. So these are two C structures that represent those classes. And then finally, value. Since Ruby is dynamically typed, we just cast everything to value all the time and never pay attention to what the types actually are. So this is a type def for a pointer, actually. And I'm going to show you what those things look like. Okay, so first let's look at RBasic. So one of the things I like about looking at the source code of the interpreter is that you can learn stuff just by reading it. So normally, if you just do Ruby all day, maybe some of the syntax doesn't make a lot of sense. But with a little bit of a literacy in a lower level language, you can learn a lot about how your higher level language operates. So here we have the struct RBasic, and it has a value flags and then a value class. So this gives us a really convenient definition of what a Ruby object actually is. It's a series of flags and then a pointer to some sort of class. Like at its core, that's all an object is in Ruby. So it's actually kind of very straightforward. And then we're going to look at our object. So our object is a little more complicated, but that's fine. So our object is one of these RBasics, so that's where the class of the object lives. And then there's this union. And the first time I saw this, I was like, oh my God, what is going on? But then once I figured it out, it's actually really cool. So I'm going to delete some of this code first because it's easier to tell what's going on without looking at this stuff. So let's focus on just this bit. So I'm going to get rid of this comment too because it's not helpful. Okay, so we have this struct embedded inside of our object, and it's got this pointer to the num IV, a value pointer to IV pointer, and a void star IV index table. And I was like, what does this mean at all? And then I remembered, oh, IV is short for instance variables. So a Ruby object that's not just part of the basic object contains the number of instance variables and then a pointer to the list of instance variables in this table. So this is kind of how Ruby stores these things, dynamically allocates based on the number of instance variables you have. Okay, that makes sense. What about this stuff that I deleted? So unions in C allow you to declare two data types together, and then you sort of just decide which one you want to interpret those bits as, and you get whatever one it is, and you just hope that you picked the valid representation and not the invalid representation. So what this union does is it unions that struct with this array of values. I was like, this doesn't make any sense. And then I thought about it. So our object embed len max is defined up here as 3. So we have 3 things or a list of a dynamically allocated list of things. Oh, Ruby has an optimization built into it where if you have 3 instance variables or less, it stores them inline. But if you have more than 3 instance variables, it has to manage this like lengthy heap. So I've kind of already learned a little weird optimization trick about Ruby. If I have, when I go from 3 to 4 instance variables, things get slower just by reading this ridiculous definition of the data structure, right? And so I don't know whether that will actually ever be useful in any context, but I have another fact stuck up in my brain that I know about Ruby that I didn't know before. So then I wondered, why is it 3? Like, why did they choose the number 3? And it turns out the reason is that uint32 is 32 bits. Value pointer is a pointer to 32 bits. Void star as a pointer will be 32 or 64 bits based on whatever thing you're using. And so this is 3 values, so it's the same size either way. So it's not like using up any space. So it's an optimization based on that stuff. So yeah, anyway, this is how I spend my weekends sometimes, just like reading random C code in the Ruby interpreter and learning like what's going on. So we have all these structures, and that's cool, but reading source code only gets you so far, and it's often tedious, especially if you don't have this like C literacy or low-level programming literacy. So you can also learn a lot about Ruby by using the Ruby interpreter to inspect it. So I wanted to figure out like what actually happens when we call the blank method in Ruby. And rather than trace through a whole bunch of C code, I want to show you some APIs that work really well here. So I have this mem.rb file. So this is just a Ruby file. And we're gonna ignore this allocate count real quick. I'll explain it afterwards. So this script does a couple things. First of all, it prints out the size of an object. So there's this really, really useful thing that I found most Rubyists don't even know about called object space in the Ruby interpreter. And what that does is that gives you an API to access the internal state of all of the objects that the Ruby interpreter knows about. So you can actually query these at runtime in your Ruby script to find out stuff. And this is much more interesting than digging through source code. So if instead of counting up the number of bytes in that object, I could have just called object space memsize of a new object and found out the size of it and printed that out. So you can do this kind of dynamic querying at runtime, and that gives you all sorts of really interesting benefits. So I just deleted this allocate count method. We're going to talk about it in a second, but some more Russian where it compares, this is the source code from that, doing the blank check. And then allocate count returns a hash of all of the objects that were allocated while this block of code ran, basically. And so there's two things in there that I don't care about, which is free and total, and then I also delete all the ones where there were no objects allocated, and then I print out here are all the different kinds of objects, and then do some math where I sum up all of them times their size to find out how much memory was allocated. So this allocate count uses another really interesting feature of the Ruby interpreter. I didn't actually write this method. I should say Aaron Patterson, Tenderlove, who works on the Rails project. I liberally borrowed this from him. But the allocate count method is really cool. So in order to figure out how many objects that your system is actually allocating, you first turn off the garbage collector by using gc.disable, which again, Ruby is so dynamic, it just lets you tell its garbage collector whatever at runtime. And then you use object space to fetch what are all the objects that are currently allocated. Then you run your block of code with yield, and then afterwards you count all the new objects again, and then you diff the two hashes, and that will actually give you, all the objects that were allocated during the run of that block. And then you turn the GC back on, because that's important, and then you return that hash, right? So this is kind of an interesting technique. I will use interesting. Again, like I said, doing stuff that's not good from an engineering perspective can teach you a lot of things. Like, this is a short-run script, so I could actually forget that gc.enable, and it wouldn't really do anything that bad. Like, this is not actually allocating that much memory. But you have these sort of tools when you can reach lower into your interpreter. So if I run ruby mem.rb, so we see that a Ruby object is 40 bytes of memory, and that in the process of doing that comparison, it allocated 54 strings, 1 hash, and an imemo. I still don't know what an imemo is. I think it has something to do with the GC internal data structures, but I'm not totally sure. That's another cool part of messing around is you don't actually have to be 100% sure of everything. You can learn iteratively and figure more stuff out over time. And it's only one object anyway, so it doesn't matter. But if we take the 54, 55, 56 objects, and we multiply those times 40, which is the size of an object in Ruby, we know that this allocates at least 2,240 bytes of heap memory. And so, that's not a whole ton, but it's still allocating stuff, on the heap, and it's making all these objects and deleting them, and it has to deal with all that garbage collection stuff. And so if we compare this to the Rust example, where we did that chars and the iterator, one of the cool things about Rust is that char is a UTF-8 Unicode scalar value, which means it's always 4 bytes, unlike 1 byte where char is in C, or at least a byte. And so what that means is we know that that's always Unicode enabled, but more importantly, char is like a native primitive type. So because Rust is a lower level language, you don't have objects with all of this, pointer to a class and all these instance variables. It's just 4 bytes, just literally 4 bytes, and that's it. And so what that means is, since we're not doing any heap allocation, we don't need a garbage collector, and in fact, Rust doesn't even have a garbage collector, but we also have amazing optimizations. So all of that stuff with the closure, Rust and LLVM put together. LLVM is an amazing piece of compiler technology. I'm so happy that it exists. It's a great way to make a new language and be able to actually compete against people who have the engineering resources of something like Apple. Like, Apple invests in Swift and Clang and makes LLVM better, and that also then makes Rust better, so, woohoo, open source. But Rust/LLVM is able to figure out, when I have this when I have this chars.rs, so it's able to say, okay, even though this is a closure, it doesn't actually close over any variables. So let's just make that into a function pointer instead. And then with the iterator, it knows, again, the same kind of thing. Like, I don't actually need to heap allocate anything to do any iterator stuff. I can just reuse this small chunk of memory. And so this ends up allocating something more like 50 or 60 bytes of memory on the stack as opposed to thousands of bytes on the heap. And that's like one of the reasons why this is so much faster, even though it feels really high level. So, so that's a really cool thing. Compiler optimizations are awesome. It also means, unfortunately, that sometimes your unoptimized build runs like really, really slowly. So there's a common thing where people will join the Rust IRC room and they'll say, hey, I heard that Rust is faster than almost any programming language, but like it's slower than my Python is. I don't understand what's going on. And we're like, did you remember the release flag to turn on compiler optimizations? And they say, oh no, let me come back. And then 5 minutes later, they're like, all right, that's 120 times faster now. Never mind. Like actually this runs in a fraction of a second instead of multiple seconds. So yeah, optimizations are magic and they're cool. And then also, being a lower level language, Rust stack allocates by default and makes heap allocation like semi-explicit, so you know when it's going on, and so you can control these kinds of things really easily. But that control doesn't come at the cost of like super complexity. Obviously, I'm a little biased. I don't think Rust is overly complex because that's why I work on it. But you know, it's not the same as like, oh wait, I mallocked this memory. I have to remember to free it. What is going on? Did I actually free it or not? Because the compiler helps you with those kinds of things. And so that stuff's all real fun. Here's the link to that C project. I knew I had a slide about it, I just put it afterwards instead of before. So let's talk about comparing that Rust code to some C code, because that's interesting. So I mentioned Discourse earlier. I'm gonna open up a new tab with this, testing the conference Wi-Fi during my talk. That's a bold move. So one of the things I love about Ruby is how flexible it is. And so this fast blank gem is written by the Discourse guys that I mentioned before. And all you have to do is require fast blank, and when you require this file, it overwrites the definition that Rails provides with its own definition, which is like extremely easy to use, but you know, also kind of like so dynamic you don't know what's going on sometimes. But anyway, so how much faster is fast? So according to its own README, it's about 1.2 to 20 times faster than the implementation in Ruby, which is cool. So here's a bunch of benchmarks and standard disclaimers about like, this is just a benchmark, don't believe me because benchmarks are terrible and complicated and, so that's cool. Also it notes this gem allocates no strings during the test, so there's less of a GC burden too, so it's faster, so that's cool. But anyway, this is written in C. And it's written by really smart programmers. Like, I'm going to show you this code, but I'm not saying this code is bad. It's actually really good code, but it's just the C stuff that makes it really complicated. So compared to that .chars, .all, .c whitespace, you end up having all of this. So we have to do this, messing with the Ruby interpreter to fetch Ruby string details. We have to deal with code point stuff. And then this is all the individual code points, apparently, that are whitespace. Except there's a special check in there for Ruby version 2.2 and stuff. And then here's the actual encoding things and whatever, blah, blah, blah. And so some of this stuff comes down to the fact that whitespace is defined in the Rust standard library, but that's not even that bad. I'm going to show you briefly what that looks like. It's here. Oh, nope. Click the wrong one. It's this one. Come on, I know I saw it down there. Sometimes grepping for code doesn't actually work. Did I click the wrong button? This is the one I want, char. Okay. So some of it is like, okay, that massive switch statement is hidden in the standard library. But even in the standard library, let me make this bigger. Instead you have, if it's a blank or it's from this list, it's true. Otherwise, if it's that one, check that if it's a whitespace property or not, it's false. So like even at its core, the part that's not in the file itself, the part in the standard library is even significantly simpler than the C. And actually, the Rust is slightly faster than the C is. which is cool. The reason why, the cheat, is that Rust only deals with UTF-8, and the C code deals with other encodings as well. But in today's world, almost everything is UTF-8 all the time anyway, so But that's why I like to say just as fast, because like it's not really about who is faster, it's about could you write self.chars.all is whitespace, or could you write this? And so like, you know, it's about the averages of if you're coming from a dynamic language, Rust is much more pleasant to use than C and gives you that, that same amount of like low-level control and speed. And so the reason, so another thing that's really cool about this, so Ruby has C extensions, naturally, which is what that code was I just showed you, and FFI. But since C is sort of the universal Latin of programming languages, every language knows how to pretend to be it. So I can actually write a Rust extension to Ruby and have the Rust pretend to be C, and the Ruby interpreter will call into it thinking that it's just C code and everything works. So this is actually one of the earliest production uses of Rust was as a Ruby gem for performance monitoring and Rails applications. And this is actually an extremely recent one too. So I titled this Rust plus Gems because this is a Ruby themed presentation, but this is actually about Python, but you know, whatever, it's fine. I saw a tweet one time that said something like, do I have Ruby or Python experience? Man, I can control any kind of gem with any kind of snake, which I thought was really silly and ridiculous. So Ruby and Python are super similar. And so there's this startup Sentry recently posted this graph, you know, with a little Rust logo rolling down the hill. But they took a hot part of their application on the server written in Python, and they replaced it with Rust instead. And this is the graph of their CPU time going down. So you can sort of see after they deployed the Rust code, it was actually such a bottleneck in their application that it made the average response time of all requests go down significantly because of this thing. So this is kind of an area where I'm seeing a lot of interest in Rust, and sort of one of my big pitches of Rust is, you know, maybe you don't do device drivers for a living, or you don't do embedded devices, or you don't work on operating systems, or even web browsers, anything that needs to be low level. But maybe, you know, you're spending a little too much money on your EC2 bill, or maybe your application is a little slow in a particular pathological case, and you can like put Rust into your other programming languages to speed them up, you know, whether it's Ruby or Python or Clojure or Erlang or anything else. And so that's lots of fun. Yeah, and so this is the processing time went down like, woo. Okay, so I promised you at the beginning that I would do some silly stuff, but this has kind of mostly been serious with maybe a little bit of jokes. So here's the really silly part. So I would like to announce my own personal fork of Ruby. I have fork emojis. So as I said, I got bored on the weekend, and when I get bored on the weekends, I do silly things sometimes. And so I have a link here. It's got 4 whole commits. This is my improvement. Improvement to Ruby is 4 commits. And what it does is it replaces one single function inside of the Ruby interpreter with Rust code instead of with C code. And then I glued them together. And part of why I did this is, you know, so oftentimes we talk about, you know, writing good, clean code so that, you know, you can like maintain it later or whatever. This is not this. And the nice thing about that is it actually lets you do things faster when you don't have these kinds of constraints. So example, the first commit here is called commit makefile. And what this first commit does is I called /configure to generate a makefile, and then I just committed it into the actual repository. Why did I do this? Because I did not want to figure out, and this is the, you know, junk that gets installed, is because I didn't want to have to figure out how to get auto tools to rewrite one file in Rust instead of in C. So Ruby has this really complicated build system that generates these makefiles, and I'm like, this patch is never getting upstreamed, so whatever. Let's just like generate it and check it in, and that's fine, because this is never going to run on anyone's computer but my own, so who cares? Whereas if this was real serious work that I was doing, I would have had to deal with and figure out auto tools, and that would have taken just as long and been far more painful than actually messing with the internals of the interpreter itself, which is like the whole point. Okay, so then I'm going to show you briefly a little bit of what the code looks like here. So this is my fix to the Makefile. So Ruby is really modular, and each of its classes is defined in its own .c file. So I said, okay, I would like to replace one function in the array class. So I need to first give it a blank rule for array.c so that it doesn't try to build it the normal way. And then I took the lines that would usually be used to build array.c, and I copied them and made array.o depends on Ruby array.c and rarray.rs. I realized that the RU nature of both languages made the naming conventions really bad, so instead of making it understandable, I just named them very similar things, and like, whatever, it's fine. So I call the Rust compiler on the Rust file and spit out a static library, and I ignore exceptions, basically. And then that's a whole other complicated thing. In Rust, we don't really use exceptions in Rust, but we kind of have them, sort of. It's whatever. But you don't want those in C because exceptions through your C code is like undefined behavior, and that just gets really terrible. So just abort if you get an exception. And then compile the original Ruby array.c file into a Ruby array.o, and then call the linker together to smash the two things together into a final array.o output. And then the rest of the build script is expecting array.o, so it proceeds on none the wiser that I've just like jammed a bunch of Ruby into this C code. So again, if this was a serious project, I would have to make this good, but it's just for fun, so I can not have to care about making it good. So then comes another bit of joy, which is actually declaring the right function signature. So I'll show you briefly what, here's the C function I decided to replace. I decided to keep it small at first. This is a function called memclear, and what it does is it takes in an array and it replaces every element of that array with nil. So all Ruby functions start with RB underscore for that namespacing. And so this takes a pointer to a value, which we know must be an array. This code does not check that invariant, of course. We could pass literally anything in here, but I'm sure it's fine. And then the size of the array, which we hope is the actual length of the array or not, but again, who knows, it's not checked. And then same thing. I'm not going to say bad things about the maintainers of the Ruby interpreter because this is good C code. The problem is that C idioms are just inherently dangerous. So while we decrement size, we dereference mem, set it equal to qnil, which is the Ruby internal name for nil or null, and then increment that pointer. So this is doing this like decrement pointer increment shenanigans, and it's very elegant and it's very straightforward, but like if you get anything wrong, this is just gonna explode horrifically, right? So like if the size is like bigger than anything, you'll start overwriting memory somewhere. If you forget to do certain of these things, it's just C. That's just what it is. I love C, but I also hate C. So here's the Ruby version, or the Rust version. So I have to do some shenanigans, it doesn't matter, but one of the most important things is we have to figure out the values that the C code is expecting in the Ruby interpreter and bind them to Rust types. So here I went and looked in the Ruby source and I found out, okay, that value thing is actually a uint pointer T type. So I just alias it so I can use the same names in my code as they do in the Ruby interpreter. And then it turns out that nil, qnil, in Ruby, Ruby has an optimization where instead of storing a full object for nil, they just have a special memory value at the end of the pointer, and that is 0x08. I do not know why it is that, but that's what it is. So we just make a pointer to those special bits flipped, and that's how nil works, which is an optimization, but also makes the code more complicated. So here's the same implementation in Rust, and I tried to transliterate it as close as possible to the original C. So while the size is not equal 0, subtract 1. So we've already made it a little more clear by splitting out, not doing the subtraction and the comparison in the same expression. We dereference and set the value equal to nil, and then we increment the pointer by 1 with this offset method. So Rust has a slightly, you can still do pointer arithmetic, but it's not just add some math to numbers. It's, we have a method that does the right thing and that kind of thing. And then this is some stuff that you need because Rust needs it. It's fine. This is like the code that happens if you would throw an exception, but we're not doing anything with it, so we just loop infinitely and like whatever, it's fine. So that's like the immediate thing. And so then I have a second commit where I was like, okay, now that I have this thing working, and oh yeah, here's the way that I know it works, by the way. So okay, so if I run make, this will build all this stuff, and it's going to sit here for like just a second, and it's going to compile all the things. and it like works, and then if you run make check, it will actually like run the tests, and the tests currently pass. But if I were to say, delete the code in RB memclear and then run make, I'm not sure if it fails to compile. Yeah, it seg faults the compilation process. So this is how I know that my code actually worked, because like not only does it compile, but then the tests pass. But originally when I was first doing this, I just tried to do the function signature, and it turns out that arrays are used a lot in Ruby code. So if you break a fundamental part of array, nothing is going to work. Okay. Anyway, back to here. So I was like, all right, I'm going to rewrite this in idiomatic Rust. I'm on the Rust core team. I've been programming Rust for a while. I know how to make this better. So instead of doing this loop, what I did was instead use an actual for loop. So loop from 0 to the for I in 0 to size. Let's not do that manual checking of the thing ourselves. Let's just iterate over those, and then we can add to the original pointer the offset, and then set that equal to nil. And I was like, I feel good about myself. Everything is, this code is much better. Look at how awesome this is. This is actually working, because like all that compiling stuff took a while in the first place. So then, of course, what's the best thing that you can do to like not to ruin your good feelings about the code you just write? Post it to Twitter. So I tweeted a link to this, and one of my former coworkers was like, Steve, what are you doing? There's an even better Rust implementation. And so Rust has this feature called slices, and I really love slices, but I don't have a whole time to talk to you about slices. But as I mentioned before in the code, in the C code, up here, we have a pointer to this array, and we have the length of the array, but they're totally disjoint. So like this is a really common pattern in C code, where you take an API and you say, here's a pointer to a list of things, and then here's the number of things that exist. But since those two things are totally disconnected, they can get out of sync. And when they get out of sync, really bad things happen. So we have this feature in Rust that's in several other languages as well. It's not unique to Rust, but it's one of my favorites, and that's a slice. And the whole idea of the slice is, if you put the pointer and the length into the same data structure, they don't get out of sync, and everything is much nicer and happier. So I can actually construct slice from raw parts mute says, hey, give me a pointer and a length, and I will turn that into a slice for you. And then that's really cool, because I can then iterate over a slice and say, hey, give me every element of the slice, and then just set that equal to nil. So now we've taken that like explicit code with doing all the decrements and the pointer arithmetic and stuff, and made this really nice loop where we just say, please give me all of the elements and set them to a thing. So not only is this like more convenient, but it's also significantly more reliable. Obviously, in this case, we're still relying on the caller to give us the right values outside of this function, but at least inside the function, we know we're not going to override and do our math wrong. So we've kind of made this significantly less error-prone inside of it. And for 3 lines of code, whatever, it's fine. Like I said, nobody's going to actually be using my my fork of Ruby in production. This is kind of my like side project. So I eventually dream of replacing all of array in Rust. I'm just going to keep this. It's already out of date, can't automatically merge, but whatever. Like I'm going to keep replacing these particular functions as a way of learning this stuff. And as I do so, I learn more and more about Ruby, and also practice writing some Rust. And so I think that having these kinds of like ridiculous, silly, fun side projects to do is a great way to learn more stuff that you can actually use practically speaking later. With that is all I have for you. Please go forth, do fun stuff, and enjoy computers for once. Thanks.